guys. So today we're talking about something called step functions, and these are another type of function that are related to linear equations. It's not exactly the same as a linear equation, but once we graph it, I think you'll see, how it relates. You also probably won't understand why it's called a step function until we make the graph together. So there's two different types of step function. There's the floor function and the ceiling function. And I know that sounds pretty informal for math. Okay, we don't usually call things, floor and ceiling and stuff like that. But I will tell you that that's sort of universally accepted. If you go to college and you're talking about the floor function, your professors are going to know what you're talking about. Okay, so these do have more formal math names, but it's pretty widely accepted that we can just call them the floor and the ceiling function. So what these things do is they take values that are decimals and fractions, things that are not nice, happy whole numbers, and they force them to round one way or another. Okay, and you'll see some applications for that as we go through the lesson. But basically, the floor function rounds everything down to the integer that would have come right before it, and the ceiling function rounds everything up. And to do this, you're kind of disregarding the rules that you've learned about rounding before. So like all of that stuff about 0.5 rounds up and everything below that rounds down, that kind of thing. This forces you to go one way or another and sort of ignore those rules. Okay? The notation for these things, by the way, and you have to be careful here because this notation can easily get mixed up with absolute value. Notation for the floor function looks like this. So it's similar to the absolute value, but it's got the little brackets on the bottom. That's what's telling you to round down. And then the ceiling function looks just like that, except the little brackets are up above. Okay, so that's what's telling you to round up. And so just make sure you pay attention to the difference between that and what we were doing yesterday with absolute value, which are just straight brackets. Okay? Okay, I'm going to get rid of my face here. Okay. So looking at some of these values that it wants us to round, this is saying to take 4.2 and round it down. So 4.2 would round down to 4. Basically, I'm shaving the decimal off of that. 5.9, even though I know it's tempting to just round that up to 6, these brackets are telling me to round down, so that's got to round down to 5. This one here is telling me to round up. It's just a little bit past 8, but the way this function works is once you step past 8, even a little bit, that automatically rounds up to 9. Okay? Now, for this next one, and a couple other here that are negative, I find that usually you need to look at a number line to really understand why this works the way it does, because they're not as instinctive as some of the other values. Okay? So thinking about like a number line, this would be 0 and then 1, 2, 3. Number line would be -1, -2, -3. If you think about where -0.7 falls, it falls between 0 and -1. So it's going to fall like right there. This is telling me to round up. Now if this was a regular, a positive 0.7, it would round up to 1. But with negative numbers rounding up, this would actually take me to 0. Okay? So just be careful. Those negative numbers run backwards from what you normally think that they do. Okay? 2 is already an integer, so it's just going to stay at 2. It doesn't round anywhere. -3.4, again, be careful. -3.4 is going to be between -3 and -4. And this is rounding down, so we want to round this way. That would round me down to -4 for that one. And so I really highlight the difference between the positives and the negatives with these two examples. 1.3, which would be like right here, if I'm rounding that up, that rounds up to 2. But then -1.3, which would be like here, if I'm rounding up, rounds up to -1. Okay? So just be careful with those negatives especially. And if you need to draw a number line as a visual, go ahead and do it. Okay. Example 2, we're going to talk graphs here. So I always start these with an XY table, although probably once you've done a few, you won't need to physically draw out the table. You can kind of just do it in your mind, but it's a good visual here. And I start with 0. You know that 0 is my favorite. So if I plug 0 in here, okay, it's going to just stay at 0. It doesn't round anywhere. And then I add 4, so my y value would come out to be 4. And so I know this graph is going to contain the point 0, 4, like that. And then I'm going to creep forward from 0. So I'm going to go to like 0.2, let's say. Well, when I plug 0.2 into this function, it's just going to round down to 0. And then I'm going to still add 4, so my y value is still going to stay at 4. And in fact, I could I could go 0.7, I could go 0.9, okay? I could even go 0.999. All of these things are going to round down to 0. And so the y value is still just going to be a 4. And so if you think about what this is going to look like on the graph, it's going to be a horizontal line at 4. But then we need to think about where that stops. The place where it's going to stop being a 4 and it's going to jump up to the next level would be as soon as I jump to 1. Because when I plug in a 1 now, that's going to stay at 1, and 1 plus 4 will give me a 5. And then from there, I could do 1.2, I could do 1.7, I could do 1 point whatever. All of those y values are going to stay at 5. And so the way we show this on the graph, how it jumps from 0 to 1, is we do a horizontal line up until 1, but then at 1, I'm going to put an open circle. Okay, hopefully you can tell that that's an open circle. Because that's telling me that this goes all the way up to 1, but it doesn't actually include 1. Okay? And then when I get to x equals 1, now my y value is going to be a 5. And it's going to stay at 5 all the way until I reach x equals 2, where it's going to jump up a level. When x equals 2, my y value would become a 6. And so once you get a few of those bars on there, you should be able to just fill in kind of the pattern there. And then you can even take your pattern and go backwards with it. It's going to look something like this. And this right here is why this thing is called a step function. Okay, because when you graph it, this is what this crazy thing looks like. Okay. Just super quick here, and again, I could continue that, but just to draw this back to linear functions, because my bell's going to ring here in a second, if I were to connect those solid dots right there, that would be the line y equals x plus 4. So it's almost like someone took a linear function and took all the little diagonal pieces and just laid them down flat. Okay? So that's what's happening in this step function. Okay? And then the other thing I wanted to talk quick in terms of graphs was domain and range. So the domain of the step function, I can put in anything I want for x. I can put in decimals, I can put in negatives, I can put in whatever. So my domain is all real numbers. But then if you look at my y values, think about what kind of y values I'm always going to have. Those are called, so some people will call those whole numbers. Technically, whole numbers are only positives. And I am going to get some negative y values in here. So negatives are allowed too. I'm going to say it's the set of all integers, because technically integers include positive and negative numbers. Okay, so the set of all integers would be your range. Okay? Okay. I want to just quick get through one word problem here. Whoops, it's right there. A bottling company prepares bottled water and packages them in cartons of 8. Write an equation to represent the number of complete cases of water the company will ship if they have B bottles of water. So I'm going to say cases of water. So W represents how many complete cases I can make. Now what I would normally do here is I would take my B bottles, and to see how many groups of 8 I can make, I would divide that by 8. But then if I have extras, if I have leftovers, I can't make a complete case out of those leftovers, and so I can't package those up. I'm not going to send out a case that isn't complete, right? I'm not going to send out a case that has less than 8 bottles. So I'm going to kind of just set those bottles aside, and my number of complete cases would be this number rounded down. And so in case that doesn't make sense to you, let's do this with a real number. Let's suppose I had, I don't know, 50. I had 50 bottles of water, and I wanted to figure out how many cases I was going to make. Okay. I would take that 50 and divide it by 8. Okay. And 50 divided by 8 gives me, let's see, 8 times 6 is 48. So I think it's going to give me 6.25. Okay. So I could make 6 complete cases, and then these represent the extra bottles that wouldn't fit in a case of 8. I don't want to consider those at all, and so I would say I'm going to make 6 complete packages of water, 6 complete cases. Okay. So, but this is really how you would answer the question over here. I was just kind of doing an example numerically here. Okay, so homework for tonight after this lesson will be posted on Blackboard for you, and we will spend some time in class tomorrow reviewing.